Now we've got some basic concepts under our belt here. It's time to dig a little deeper into dynamical accounts and see what emerges with these basic tools. One thing we've noted is that the properties of a dynamical system may change abruptly at some critical value of a parameter. We saw this, for example, when gravity switched from being an attractive to a repulsive force. When the attractor layout of a system shows a discontinuous change as a parameter is smoothly varied, we speak of a bifurcation in the system. That usually means that where there was one option, there are now two. A complex system may have many attractors, but this speaks of a qualitative change to the attractor layout. When this happens in a system that is well modeled as a dynamical system, a real physical system, then it's usually the case that before we see any such bifurcation, any such qualitative reorganization of the states of the system as a whole seems to get wild. This is called critical fluctuations. The effective dimensionality of the system goes up, explodes. It may go from looking like a 5-dimensional system to looking like a 500-dimensional system and then back down again. This is a common feature of the reorganization of any complex system. For that reason, we find similar kinds of evidence of critical fluctuations in lots of systems where the causal underpinning is completely different. So you know critical fluctuations from the notion of an earthquake. An earthquake is a critical fluctuation, as the underlying system is very simply described when it's in a state of tension, and an earthquake results when that tension shifts and one plate moves abruptly with respect to another. So we're shifting from one equilibrium to another equilibrium. But in between, of course, things go wild. This increase in dimensionality seems to be necessary for a system to move from one more or less persistent state to a qualitatively different, more or less persistent state. And we can show that the causal underpinning can be of many different kinds. We see the same thing in stock prices before a market crash. So we have a couple of 100 years of experience of this, and you may think of a stock market crash as being an occasion when the prices of stocks go from a high level to a low level. But that's not what actually happens. What actually happens is that they become highly volatile before suddenly transitioning to the lower level. And this volatility is well known. There are many economic indices of volatility. This is precisely what they're looking out for. Critical fluctuations might also be seen with the radical change in our forms of social organization introduced by the virus recently. An alteration to the conditions of our living has affected a qualitative shift from one form that we used to call normality, remember, and we're heading to what we now call the new normality. This business of transitioning from a normal to a new normal inevitably requires a period of chaos. We know this from war as well. Getting away from such, I should say a word about the word catastrophe. Like chaos, catastrophe is a word which is in common use, and it means something terrible. Within the field of dynamical systems, there's a precise meaning for catastrophe, and a catastrophe refers to this precise situation where a system reorganizes from one relatively persistent and stable state to another relatively persistent and stable state, abruptly, with an increase in dimensionality in the meantime. There's a whole branch of dynamical systems devoted to catastrophe theory, associated with the French René Thom. Now, we'll be playing just a little bit with dynamical systems. We don't have a lot of practical hands-on stuff to do here. What we're trying to do is learn the concepts with which people who employ this vocabulary attempt to make such things as human behavior intelligible. what we can do using our little simulator is we'll be exploring in Lab 7. We can induce a limit cycle attractor into a simple recurrent network. It will start almost any set of weights for the network shown at the bottom left there, a simple recurrent network with just 3 hidden units. Almost any set of weights will mean that if you present constant input, you'll get constant output. So if you present a never-ending stream of ones at the input, you get a never-ending signal at the output. But it is possible to find weights in which the behavior qualitatively shifts so that constant input produces oscillatory output. That's a shift from a point attractor to a limit cycle attractor. So we'll be doing that, and you'll be making smooth, gradual changes to the parameters that define the dynamical system. Those are the weights. And looking for the point at which the qualitative behavior of the system alters, where it goes from doing one kind of thing, a steady state output, to a different kind of thing, oscillatory output. What you're actually doing there is you're hunting for a bifurcation. So that'll be fun in lab. There's a very simple discrete dynamical system that illustrates very many interesting properties. And this is known as the logistic map. You may have seen these kinds of diagrams before, and we're going to play with this as well. The logistic map is a discrete dynamical system in one dimension. It's got a remarkably simple equation, which is shown here. The state of the system at time t+1 is some constant or multiplied by the previous state multiplied by 1 minus the previous state. Now that's very, very simple, and the only thing we're ever going to vary here is or. That is, we will look at the behavior of this system for different values of or. What we'll find is it doesn't really matter where we start. The initial conditions don't seem to matter terribly much here. At least until things get really complex. But the qualitative behavior is determined precisely by the value of or. There is an app which I have co-opted from Joshua Garland and Santa Fe, which is available for you to play with. And I suggest watching this video first before you go off, and then I suggest spending some time playing with this, because it illustrates many of the concepts that we have discussed so far. So you'll find point attractors, limit cycle attractors, loads of bifurcation, plenty of chaos, lots of sensitivity to initial conditions, and so on. The logistic map, as presented in this app, works in a very simple way. And there's a very helpful graphical element which is used to quickly demonstrate graphically the long-term behavior of the system. The two-dimensional plot on the right-hand side shows the state at time t and the state at time t+1. And the parabola, the brown parabola there, is the curve given by the logistic map. So to iterate the system, we start with some value at x of t, and we go up to that brown curve, and then we go to the left over to the y-axis and find out our new value. Then we take that new value and we plug it back in as x of t again and go find the next value. Now all that shifting from the y-axis to the x-axis can be neatly circumvented through this one quick trick. We draw the blue line y equals x, and now when we take our first value, let's start with the left-hand side of that red curve, and we go up and we find the value at t+1. Instead of going to the left to the y-axis and then copying it down to the x-axis and then going up again, we can take a right turn instead of a left turn to the blue line, and then we go straight up again, and that gives us quickly our next state, and we can iterate this procedure. So that means we have a very quick way using this graphic to see what the long-term behavior of the system is. Now, for a specific value of or, and for a specific starting point, we can conduct many iterations, and the system will settle down into one or other attractor. There are several attractors available. At or equals 2, for example, the system will settle to a single point attractor. The bifurcation diagram which is shown at the bottom of this, shows the final state over the long term for the system, irrespective of starting point, for specific values of OR. So, with an OR below 3, you'll find that the system settles down to a single value, and that's the thin line coming in at about 0.6 and going across. Then as we pass a critical value for OR, we find that the system displays bouncing back and forth between two values. This is the equivalent in a discrete dynamical system of the limit cycle attractor in a continuous dynamical system. And you can see that for between about 3 and about 3.4, the system displays two values, and as we gradually increase OR, those two values gradually diverge. And then it gets funky. And we'll look at what happens later on in that plot as we go along. So the point attractor looks like this. Here's a value of OR equals 2.6. And you can see, you can follow the red curve on the left-hand side, which starts with an initial value of 0.2. And you can see that the system quickly settles down to that point attractor at the place at which the blue line crosses the brown curve. The right-hand side shows the evolution of this in time, and you can see that the red dots converge to a stable value. Furthermore, here we can see that it doesn't really matter where we start, we get the same behavior anyway. These plots are called cobweb plots, and they're just very helpful for illustrating the long-term behavior of the system. Let's go to a different value. At OR equals 3.2, we see this value, this behavior. Again, we're going to start with x equals 0.2, and that quickly settles down into a period 2 attractor, bouncing back and forth between two values at about 0.5 and 0.8. As we go up, at OR equals 3.5, here's a period 4 attractor. Try follow it around. You can even do this with your finger just by starting somewhere on the x-axis and doing this business of hit the brown line, hit the blue line, hit the brown line, hit the blue line, and you can quickly verify for yourself that this is a periodic period 4 limit cycle. Once we go a little higher, things get seriously funky. At 3.7, here's a chaotic attractor. And as you go to play with this, I encourage you to explore these chaotic attractors and explore the changes between the various forms of long-term behavior. Remember, chaos does not mean random, even though this looks random. This is a deterministic dynamical system, but it is inherently unpredictability. And when we are in a chaotic regime, the exact trajectory that the system traces out will depend sensitively on initial conditions. When we had a point attractor or a limit cycle attractor, that was not the case. Pretty much all starting values, I think all starting values, will go to that simple attractor. When we hit the regime of chaos, however, two trajectories that start arbitrarily close will ultimately diverge. Here's an example. At OR equals 3.9, we're well into the chaotic regime here. And we start off with 2 points almost identical. One starts at 0.5 and one at 0.50001. And you can see that by about the 40th iteration of this, the two trajectories have diverged. And you can follow this for yourself by playing with the app. So when the behavior of the system as a whole goes from a point attractor to a limit cycle attractor, or from a limit cycle attractor to chaos, or the other way, we speak of a bifurcation. Bifurcation implies path splitting, that you're now going to go down one road or the other, but the attractor diagram that you see in the bottom left suggests very clearly why it got this name. So this system exhibits a specific kind of bifurcation called a pitchfork bifurcation, where a single attractor splits into two. And what happens then is that each of those splits into two and each of those splits into two. So the bifurcation diagram for the logistic map should now make sense. Now we're just going to turn our attention to the craziness on the right-hand side of this. You can see that there's a lot of gray, but there seems to be regimes in which the system becomes simpler again. And if we zoom into one of those, here we have the blue points come from 100 generations of the logistic map for 1,000 different values of OR. The different values of OR go from 3.7 to 3.9, so very finely sampled. And the blue illustrates where the trajectory goes for 100 iterations of the system. And you can see that indeed, while in general it's very, very complex, there are patterns within patterns here. Now, we've broached the topic of chaos. Many of you will have met the notion of a fractal before. You may have even played with the Mandelbrot set. The logistic map, the attractor layout of the logistic map, has indeed a fractal characteristic, which means it's self-similar at all scales. I'm going to play this with a slightly annoying piano music, and we're going to dive into the logistic map. The actual numbers are given there. So we're going to explore some detail and blow this up to see what lies hidden. There's basically the structure of the whole map repeated at a much finer resolution. We zoom in on that and we find it again and again, slightly warped, but preserving the same essential structure. Because this is an abstract mathematical object and not a real physical system, this goes on infinitely. If you've never met fractals before, they're some of the most beautiful mathematical patterns around, in which really complicated structures are generated from very, very simple generating equations. And one of their strongest characteristics is this notion of self-similarity at all scales.